So welcome to a continuation of Chapter 2. We were moving on to acceleration. Acceleration's the rate at which velocity changes. Anytime you describe something as a rate of change, you're going to have time in the denominator. Acceleration's a vector. That means it has a direction and a magnitude. When you are slowing down, you say you're decelerating. Normally, we think of deceleration as a negative acceleration. It's trying to pull you in the opposite direction that you're going in, and so it slows you down along the way. You can see as we move down and look towards the bottom of the screen that the formula for acceleration, in this case, since we're dealing with the definition of average acceleration, is a bar equals delta v divided by delta t, and delta v becomes v final minus v initial if you expand it, divided by t final minus t initial. We probably are going to take that a bar and just write it as an a. All of the accelerations we're going to deal with are average accelerations, and so we don't have to differentiate between the two. So deceleration always means slowing down, and if your direction of travel is positive, that means your deceleration is going to be negative. Typically, a negative acceleration means you're slowing down. So let's look at figure 2.14 from your book. It's a little graphic showing you a car and the relationship between its velocity and its acceleration. So if the car is going to the right, the green arrow indicates the velocity, the purple arrow is the acceleration. So in the right, it's speeding up. In the middle diagram, it's slowing down. In the third diagram, the car is going left and the acceleration is going right. So it's still slowing down. And then in the last direction, the last diagram, we've got the car and the velocity going in, with the acceleration and the velocity going in the same direction. And you can see there's a little descriptive box out to the side that describes all four cases in a little more detail to try to help you out. So you can have a positive velocity and a negative acceleration, or vice versa as you go along. So we will define the direction your object moves in. Usually we're going to prefer to define that as the positive direction. What that means is that any negative acceleration will be a deceleration and you'll slow down. If we look at this next graphic, figure 2.21, it shows us the relationship between various graphs, position versus time, velocity versus time, and acceleration versus time. And again, there are explanations out to the side because I'm probably going to go a little quickly in our discussion of it. So in position versus time, you can see have position on the vertical axis and time on the horizontal axis. We start out kind of slow, then we pick up speed, and then we're slowing down again as our position gradually changes. Here, change is fairly rapid in the middle, and it slows down on the edges. If you look at velocity versus time, this first half says that we've got a fairly rapid change. That's this part of the graph. The middle part says the velocity is changing at a constant rate, and then we're slowing down relatively quickly. And then finally, you can see how the acceleration changes as you go along. So if you have the velocity at a constant rate, you'll notice that your acceleration goes to 0. If you have your velocity changing at a constant value, then your acceleration is going to be a constant. And you can see how it flips as we go along. Positive changes in velocity give us positive acceleration. Negative changes in velocity give us negative acceleration. So let's look at some of the motion equations that we need to have for our analysis of motion in one dimension. You need to memorize the average velocity equation. It is that delta x over delta t is going to give you the average velocity. And remember that delta x is x final minus x initial, and delta t is t final minus t initial. Now, we can take that equation and get rid of the first equal sign and just have delta x over delta t. And we talked about the fact that your average velocity, if it changes in a regular manner, would just be final plus initial over 2. You will find this a very useful equation. Many times they'll give you initial velocity and change in time and change in position and ask you for final velocity. Or they'll give you final and initial velocity and time and ask you for how far did the object travel. This is going to be a very important equation. You need to memorize it. The next equation that will turn out to be very important for us is acceleration. So acceleration is change in velocity over change in time. So v final minus v initial over t final minus t initial. So acceleration is change in velocity over change in time. You need to memorize this one. The third equation we'll use a lot is typically written as x equal x0 plus v0 multiplied by t plus 1/2 multiplied by a times t squared. X is your final position, x0 is your initial position, v0 is your initial velocity. T in this case is really delta t, it's our change in time or our total time. 1/2 is just 0.5. A again is your acceleration, and t squared is the square again of that total time. Sometimes this confuses people, and so we probably will start writing it as delta x, which is what you'd get if you just subtracted x0 from both sides. X minus x0 gives us delta x. So delta x is equal to v0 multiplied by t plus 1/2 at squared. Notice that I put things in parentheses. You really, really, really need to do that so you can keep up with the subscripts and the units when we write things down and just exactly what's being squared. If you leave the parentheses out, sometimes you think you have to square the whole thing when it's just the time that's being squared. So keep up with those parentheses. There are other equations. Some people also look at these equations. You have x equal x0 plus v bar times t. That's just a variation of the v bar equation. If you go back and look at it, it's just been rearranged. Some people like v equal v0 plus at. That's again just a variation of the acceleration equation. They just left out the subscript f on the v and the x. And some people like this last equation, and it's just a combination of the first and the second equations. So you don't need to memorize these three. You can do everything we want with the ones I've given you above, the acceleration, the delta x, and the one where you have v final plus v0 over 2. So those three equations are very, very helpful. Let's look at some problem solving strategies. In physics, you need to be very careful how you solve a problem. There is no such thing as scratch work. We're going to organize everything and write it out. It is probably the only way to find your mistakes when you make them, and it's the only way for me to follow what you did. And for me, it's just as important to know the process you took to solve the equation as it is to get the actual answer. So you're going to read the problem. If you think you need a picture, draw a picture. You must make a table of what you know, what you're trying to find. So knowns and finds, we'll do some examples. And then you need a column for your formulas. Don't write down the formula that you think you're going to use. Just write down all the ones you know. And that way they're right there in front of you. And when you need them, you'll be able to look at them and just go down your list. It's too difficult in the middle of a problem sometimes to pull the right formula out of your brain. And so then we'll have a strategy. We'll look at our first formula and try to use it. If it doesn't work, we'll move on to the next one. When you've gone down your list and looked at every single formula, you should be able to figure out the answer to the question. I think we're going to stop with this, and then we'll pick up with our examples in the next video. So we'll stop our share. We'll